We're in our final unit called Electrochemistry. According to the MyAP, this is in Unit 9. An overview of electrochemistry. So we're going to go over oxidation numbers. We're going to identify redox reactions. They are reactions that have a transfer of electrons. It's almost every reaction, but not everyone. We're going to balance redox reactions using the half reaction method, calculate the EMF, compare and contrast voltaic, also called galvanic and also called electrochemical cells, and electrolytical cells. We will predict spontaneity, thermodynamic favorability from cell potential and G, and we'll calculate quantities, mass, current, time, charge, number of moles of electrons transferred. So oxidation numbers, we learned about these in first year chemistry. You have to assign the oxidation number or be able to identify the oxidation number in lots of compounds. So oxygen is almost always 2 minus unless it's with a peroxide. And if it's with a peroxide, it's -1 because the hydrogen is a +1. And hydrogen is +1 unless it's with a metal, meaning a metal hydride. Then it is a -1. And I've seen this on an AP test before. And an element by itself, if it's just written like Na, O2, or Cu, it has a charge of 0. And an element with the charge has that charge. So if you see Fe3+, it has a charge of a +3. Let's do some oxidation number practice. So in HNO3, you would do the O is a -2 because that's what it normally is. H is a 1+, and then you figure out what the N is. And just like in first year chemistry, we work from the outside to the inside. So the oxygen is 2 minus times 3, so that's a -6, and we have a +1. So nitrogen must be a +5 so that it adds up to a 0. And then we go to CuCl2, that's a -1. So 2 times -1 is -2. Copper must be a 2+. And some of these just follow the old rules, like the reverse crisscross. Br2 is written by itself, so it's 0. Ag has that 1+, so it's a 1+. And PbSO4, you work from the outside to the inside, and there's a couple different ways you could do this. I would do that's a -2, and 4 times -2 is a -8. In my head, I see the -8. Lead, you could figure out what lead is because you remember that SO4 as a unit is a -2, so lead must be a +2. And let's get rid of that -2 there. And so if lead is a +2 and that oxygen's a -2, so we have that mystery number in the middle, and these must all add up to 0, so that must be a +6. So if sulfur was a +6, you'd have 6 and 2 make a +8, which would then cancel out a -8 to give you 0. Redox verbiage, or some vocabulary here. Oxidation, reduction reactions involve a transfer of electrons. The oil rig, most people prefer this. Oxidation is loss of electrons. Reduction is gain of electrons. So oxidation is loss. Reduction is gain. I prefer Leo the Lion Goes Grr, which is loss of electrons is oxidation. Gain of electrons is reduction. And let's go over, review some of this. So if you lose electrons, you become more positive. That doesn't mean you necessarily are positive, but you become more on the positive side. And if you gain electrons, your oxidation number becomes more negative. It doesn't mean you are negative, but it's going in the negative direction. You also need to be able to identify the items that were oxidized and the items that were reduced. And so we have to look at the oxidation numbers. So oxidation number of nitrogen is 0, and the oxidation number of hydrogen here is 0. And on this other side, the hydrogen is a +1. I don't know where I'm getting that crazy color from, sorry. And that would mean that nitrogen's a -3. This is a little better than that color you can't see. And so I track nitrogen. Nitrogen went from a 0 to a -3. It became more negative, so it gained electrons, and gain of electrons is reduction. And then the hydrogen went from a 0 to a 1+. It lost electrons. Its number became more positive. So loss of electrons is oxidation. So the hydrogen was oxidized, and the nitrogen was reduced. You also need to be able to balance redox reactions, and you've already done some of these. We did them in first year chemistry. So the first step for a difficult one is to write separate half reactions. One will be an oxidation half, one will be a reduction half. You balance all reactants except for hydrogen and oxygen, and then you balance oxygen using water, you balance hydrogens using H pluses, and then you balance the charge using electrons. You make them equal on both sides. And you make them equal in both halves because you got to get rid of them. You can't have them in your final equation. And then you add the equations and cancel identical species. Check that charges and elements are balanced. And for basic, you add enough OH to both sides to neutralize the solution. And the reason that you have water and hydrogens in there is that most of these happen in an acidic solution, and they have to happen in some type of aqueous solution, and hence there's water in there. So let's try practice balancing this redox reaction. So we have HOCl plus NO makes Cl2 plus NO3. So we'll break it into two halves. There are halves that have similar stuff in it. So HOCl goes to Cl2. It's really the Cl that we have in common. And we'll take care of the H's and the O's with waters and hydrogens. And the other part that had stuff in common was the NO part in the NO3. And then we take the HOCl part to Cl2, and we first of all try to balance the Cl's. So we put 2 there, so we get 2 Cl's. And then we do the oxygens by balancing water. So we have 2 oxygens, so we'll put 2 waters over here because that gives us 2 O's, and then that introduces hydrogen, so 2 times 2 is 4. And so we will have to add, I think I have a mistake over here. Nope. 2 hydrogens plus 2 hydrogens is 4 hydrogens, and then we have to balance the charge. It has to be equal on both sides, just not necessarily negative or positive, just equal. And so on this side we have a total charge of a 2 plus, and on this side we have a total charge of 0. And so if this side is 0, we got to make this side 0, so we'll add 2 electrons here. And if we are correct in this equation, in that next one, the electrons should be on the opposite side. And so in this one we have NO goes to NO3, 1 N, 1 N, 1 oxygen, 3 oxygens, so we'll add 2 waters over here, so that gives us 2 plus 1 is 3 oxygens, and then we have 4 hydrogens, so I added 4 plus hydrogens here, and then the charge on this side is 0, and an indication from up here if the electrons were on this side and we are correct on this equation, they should be on this side. And so we have a 1 minus and a 4 plus. That's a total of a 3 plus. So we need 3 electrons because that would give us 0 to match that side is 0. And then our electrons have to match. So that one's 2, that one's 3. 2 and 3 have 6 in common. So we'll multiply this whole thing by 2, and then we'll multiply that whole thing by 3 and distribute it out and combine like terms and get rid of like terms. Sometimes you have to add waters and H's. And that is the final answer. The next skill we have to accomplish is calculating EMF, and EMF stands for the electromotive force, also called cell potential, E subscript cell, and the unit is voltage, so 1 volt equals 1 joule of work per coulomb of charge, and can measure this with a voltmeter. And we will use the standard potential chart, and it would be given to you on the AP test, and now I don't believe they give you the full chart. They actually break out pieces you need for whatever question they're asking you. So the potential of the cell is the potential of the reduced and the oxidized. And we want the E cell, so that final number, to be positive. Otherwise, we don't get useful work out of it. And so if you remember from Gibbs free energy, spontaneity with Gibbs free energy is a minus G, and spontaneity with this is a positive number here. So it's really easy to do. You just look up the 2 different equations. They're both written in the same format, and you'll have to flip one, and you flip one such that when you add the voltage numbers, you get a positive number. Here's an example of a standard reduction potential chart. They're actually pretty cool how they're organized. Up at the top, we have the strongest oxidizers, and they go down to the weakest oxidizing agents. And so you notice the electrons are always written on this side, and then it makes something and it gives you a voltage. So when you look at these charts, the electrons will all be on the same side, but when you calculate an E subcell, you will have like one equation this way, and then you'll need to flip the other equation such that the E's are on the opposite side. And so if we did have silver and this iron, we would need to flip the iron one, because if we flipped it, it turns into a negative, and then if we had 0.8 plus a negative 0.77, we'll get a positive value. You wouldn't flip the silver because then you wouldn't get a positive value, and we need a positive value for a spontaneous reaction to occur. And another way to look at this is notice fluorine's at the top. Fluorine will never ever give up its electrons. It has a really high electron affinity to attract electrons, and so that is why this one's a really positive number, and it has the largest voltage on there. And then as you scroll down through this, we get to magic arrow down here. In fact, you notice that there's a change right there. These ones want to gain, they don't want to gain electrons, they want to lose electrons. So these are metals that tend to lose electrons, and that's why if they're gaining that electron, there's a negative number. They tend to give them up to the nonmetals. So let's do one of these. I find these to be kind of fun and easy little problems to solve. And you will possibly get some of these on the AP test, and they should be easy to calculate. So this one says calculate the E cell for the following reactions. So zinc plus copper 2 plus makes zinc 2 plus copper solid. So you're starting with this solid zinc, and it must lose electrons to become a zinc 2 plus, and those 2 electrons are gained by that copper ion to become solid copper. And so you look on that chart, and they're written in this direction. Zinc will say this, and it'll say it has a minus 7.6. And then copper 2 plus is written in this order, and it has a 0.34. So we have to add these together, but one of them always has to be flipped, and we flip the one such that when you add these two numbers together, it's a positive number. So if we flip the copper, we would have a minus 0.34, and then a minus 0.34 plus a minus 0.76 would not add up to a negative number. That tells us then we need to flip this equation, which we'd have a positive 0.76, and then we add the 0.76 and the 0.34, and we get 1.10 volts. And note on the reduction potential sheet that hydrogen has a value of 0. This is the baseline for all other potentials. As mentioned in the other slide, the hydrogen is the standard electrode. It's the reference for all their oxidations. The E blah 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 is 0, and that mark that we've seen before indicates standard states of 25 degrees Celsius, 1 atmosphere, 1 molar solutions. Clearly, we're going to deviate from standard states at some point in time. In a galvanic cell, also called an electrochemical cell, that's the most modern terminology for it, you will have an anode and a cathode, and they're not always written in this order. The anode isn't always on this side, the cathode isn't always on this side, but when you look in a textbook, the anode's always on this, almost always on that side, and the cathode's almost always on that side. And as I've said again and again, in college and the AP test, what they love to do is flip it up such that they won't tell you, but the cathode is sometimes on that side and the anode's on that side, and they want to see if you see what's going on. And so the anode, what I remember is anox red cat. Maybe we should write the red cat in red color. So at the anode, you get oxidation, so there's a loss of electrons. At the cathode, it's gaining electrons, so you get reduction. So someone loses and someone gains. So in this example, at the anode, electrons are being lost, and they're going to go up through here, and this is like a voltmeter, and this reaction is 0.76 volts. And the electrons keep going, and they're gained over on this side, and so it's the cathode, and this side is reduced. When we were looking at that previous slide, I pretty much said what was on here. At the anode, oxidation is loss of electrons. Electrons are pushed away. At the cathode, reduction is taking place. The electrons are being pulled there. And again, I use anox red cat. And on the previous slide, you can see what the reaction was happening at the cathode and what was happening at the anode. So galvanic cells generate electrical energy from a redox reaction. They are also called voltaic cells. Think of batteries. Don't confuse these types of cells with electrolytic cells. Electrolytic cells do generate electrical energy, but there's an outside electrical current that is put into that to make that happen. I get confused with these because they all seem to start with the letter E. Hopefully you will not. So applications of redox or galvanic cells or electrochemical cells: moving electrons equal electric current, and it helps to break the reaction into two halves. So we've already looked at how you break them into two halves and use that standard reduction potential chart. In the same mixture, the reaction happens without doing useful work, and if the solutions are separated, they can do useful work. So if they're in the same beaker, blah, nothing happens, but if you separate it, you can get useful work. We're all about the useful, spontaneous work. So if you had a reaction like this, it was connected in this way, and you just had this, and it went to there, it grinds to a halt because charge builds up. We kind of have to have a circular thing going on here, and when we get to that next slide, we'll see. So here's a galvanic cell, or again, a voltaic cell or electrochemical cell, and we need this thing called a salt bridge. It allows the current to flow. And so as the electrons go that direction, this salt bridge will allow the current to keep flowing. Since this one, we'll get into it, that one, electrons are going this way. Electrons need to be replenished over here, and then positive ions need to be replenished from that side. So here we get electricity traveling in a complete circuit, and the salt bridge helps to maintain a zero net charge. Another type of galvanic cell is one with a porous disc. I've never seen beakers like this, but it would be so cool to see that. The anode is negative in galvanic cells, and the cathode is positive in galvanic cells. And I think of, on this side, since it has the electrons, I know the electrons are moving away from it. That's why it's negative. And this one's positive because it's the cat. Remember, the cat in there has a T, which is like a positive. So if one is negative, the other one is positive. This is reversed for electrolytic cells. Line notation. You'll see this interesting line notation. So the solid, aqueous, double lines, aqueous, solid. And so the anode is always written on the left over here, and the cathode is written on the right. The single line differentiates the different phases, and the double line represents the porous disk or the salt bridge. So really, like, that's the cell on the left, and that's the cell on the right. You always write it this way in line notation, but again, if you see a diagram, they could be flip-flopped. Now, all the substances on one side are aqueous, use a platinum electrode, inert, good conductor, include all concentrations. So here's solid copper, it's becoming aqueous, copper 2+, and it's 1 molar. And then the iron 2+ is 1 molar, and you also have iron 3+ in there, which is 1 molar, and you have a platinum electrode. So write the standard line notation for the following cell at standard conditions. So remember, we go solid, aqueous, aqueous, solid. So if we have chromium 3+ plus Cl2 makes Cr2O7 2- plus Cl, we have to identify what's the anode and the cathode. I sometimes like to just pick the single thing out here. It's a 3+, and it must go to, oh my goodness, that must be a 2-, which is a 14, so that must be a +6. So it becomes more positive, so it's oxidized. Anything oxidized is at the anode because it loses electrons. Therefore, the Cl2 thing, actually that would have been the easier one to figure out, goes from a 0 to a 1-. It gains electrons. That's at the cathode. So now we write this in the notation. So we use platinum for both electrodes since they are aqueous and one is gaseous. So platinum, and then we do the Cr 3 plus 1 molar, and we also have the Cr 2O7 2 minus, which is 1 molar, and the H plus, which is not in there at all. It must be in an acidified solution to make this happen, which is 1 molar. I don't think you would know that unless I told you. Cl2 is at the cathode, and it's a 1 minus, and then Cl, and again a platinum electrode. So let's recap the galvanic cell. The reaction always runs spontaneously in the direction that produced a positive cell potential. So again, we have to have a positive number when we add those values up from the standard reduction potential chart. And 4 things for a complete description. You have to have the cell potential of the E cell, the direction of flow of electrons, so which way they go, and designation of the anode and the cathode, and the nature of all the components, the electrodes and the ions. So let's try one more galvanic cell practice. So completely describe the galvanic cell based on the following half reactions under standard conditions. So we have this cell that has a 1.51 volts, and notice the electrons are written on this side, and we have this one which is minus 0.44 volts. Again, the electrons are written on the left-hand side. So in a working galvanic cell, one of these reactions must run in the reverse direction. So we have to flip-flop one of these. The electrons must be on the opposite sides, and we will flip one. So which one will we flip? If we flip that one, we get a positive and a positive, and those added make a positive. But if we flip the top one, you'll have a negative, and that won't be a spontaneous reaction. So we must flip the bottom reaction. So we flip the iron reaction. So we have this one going that way, we flip that one, and then we add those up, and we get a positive 0.195 volts. In the line notation, since, let's go back, this one again has to be the anode on the left-hand side of those double bars, and we flip this one, so anox is loss of electrons. So if you see electrons on the right-hand side, this is the one that's oxidized. If you see electrons on the left-hand side, that's the one that gained electrons, and it's the one that's reduced. So we put this one on this side, and we put that one on the other side. Let's do a little bit more detail on the potential sheet. So at the top of the sheet of the chart are the elements that want to gain electrons or be reduced. These tend to be nonmetals and tend to have high ionization energies. And at the bottom of the chart are the elements that want to lose electrons or be oxidized. These tend to be metals and tend to have low ionization energies. Note that lithium wants to lose its 1 valence electron more than the other metals listed above it. So more on the potential sheet. An element can reduce something if it is below the other element on the potential sheet or has a more positive or more negative E number, and an element can oxidize something if it is above the other element on the potential sheet, meaning it has more positive E number. So let's try a little bit more practice. So if I were to ask you, can Fe3 plus oxidize I minus? So you look up these two things on the sheet. So you have Fe3 plus and I2, and the E's are both on that side, and you get a plus and a plus. If you were to flip this one, you wouldn't have a reaction, but if you were to flip this one, you'd get a reaction. And so the E of the cell is 0.23. We have a positive value. So yes, because the potential value of iron is above the iodine minus value, you get a reaction. So another question is, can hydrogen gas reduce silver? So H2 loses and silver gains. So yes, the hydrogen is 0 and the silver is that. Just a little bit more here. Batteries are galvanic cells. You have car batteries, which are lead storage batteries. There's dry cell batteries. There's alkaline batteries. There's NiCad batteries. And corrosion is also a redox reaction. Rusting is a spontaneous reaction of oxidation, loss of electrons. It's a process of returning metals to their natural state, the ores from which they were originally obtained. And most structural metals have reduction potentials that are less positive than oxygen, meaning they love to lose electrons. And the reaction is spontaneous, and it happens in 2 places. And salt can speed up this process by increasing conductivity. Salt on The roads in the winter, for example, in the Midwest, those cars tend to rust more than our cars do. So how could you prevent corrosion? You could coat something to keep out the air and the water. Galvanizing is a great way to do that, a zinc coat. Zinc has a lower reduction potential, so it's more easily oxidized than the iron. You could alloy metals that form oxide coats. Cathodic protection, attaching large pieces of an active metal like magnesium that gets oxidized instead. And zinc is used in hot water heaters to prevent the corrosion of the tank. So next time we'll get into some free energy and redox reactions. Yay for us. I hope all is going well, and I'll see you next time.